Generative reward models, or large language models, as judges, are increasingly used in reinforcement learning with verifiable rewards. These models evaluate answer quality, but are vulnerable to superficial manipulations, such as non-word symbols and reasoning openers, leading to false positive rewards. This presentation will explore these vulnerabilities and propose a robust solution. Large language models, LLMs, are favored over rule-based metrics for complex reasoning tasks. They compare candidate answers to references, but are vulnerable to non-word symbols and reasoning openers, leading to false positives. This highlights the need for robust solutions to ensure reliable evaluations in reinforcement learning with verifiable rewards. Systematic vulnerabilities in large language models and datasets are evident, with high false positive rates from simple hacks like reasoning openers. Proposed master RM model, however, maintains near zero false positive rates, showcasing its robustness. This highlights the need for more reliable large language model-based evaluation methods to ensure the integrity of artificial intelligence systems. RLVR leverages large language models to replace rigid rule-based functions, guiding policy model updates. However, vulnerabilities in large language models can lead to collapsed training, as seen when response lengths drop sharply, indicating failure. This highlights the need for robust solutions to prevent reward model hacking, ensuring effective learning and reliable generative reward models. Short superficial responses often receive positive rewards, revealing a systemic weakness in generative reward modeling. This vulnerability affects both task-specific and general-purpose models, compromising their reliability. Addressing this issue is crucial for improving the robustness of large language model-based evaluation methods in reinforcement learning with verifiable rewards. To address vulnerabilities in generative reward models, article propose a data augmentation strategy. By truncating outputs to retain only the first sentence, we treat these as negative samples. This approach significantly reduces susceptibility to superficial manipulations, enhancing model robustness across various benchmarks. This method is crucial for developing more reliable large language model-based evaluation systems. Critical vulnerabilities in large language model judges are evident, with systematic evaluation revealing inference time strategies as unreliable. These models across datasets are susceptible to superficial manipulations, such as non-word symbols and reasoning openers, leading to false positives. This poses a significant threat to core algorithmic paradigms relying on generative reward models, necessitating robust solutions. Rule-based rewards rely on fixed criteria, while generative rewards harness large language models' potential. Despite advancements, vulnerabilities remain. Generative models, though flexible, are prone to superficial manipulations, leading to false positives. This highlights the need for robust solutions to ensure reliable evaluations in reinforcement learning tasks. Research reveals vulnerabilities in large language models as judges, where response ordering and adversarial phrases can skew judgments. Non-word symbols and reasoning openers often trigger false positives, highlighting a systemic issue. This poses a threat to core paradigms like rejection sampling and reinforcement learning with value-based rewards, necessitating robust solutions to ensure reliable large language model-based evaluations. Master keys, acting as adversarial patterns, exploit critical vulnerabilities in reward modeling mechanics. Non-word symbols and reasoning openers like thought process can trigger false positives, undermining large language model judges. This systemic weakness affects core paradigms like rejection sampling and reward learning via rejection, necessitating robust solutions to ensure reliable large language model-based evaluations. Training robust reward models involves augmenting datasets with adversarial-like responses to counteract hacks. This approach significantly reduces false positive rates, achieving near zero levels. By incorporating these adversarial examples, proposed methodologies enhance the model's resilience against superficial manipulations, ensuring more reliable performance across diverse benchmarks. In presented experiments, Authors observed that false positive rates, FPR, vary significantly with model size. Larger models tend to exhibit higher false positive rates, especially when sentences similar to master keys are used. This highlights a critical vulnerability in generative reward models, where superficial manipulations can lead to incorrect positive judgments. Understanding these patterns is essential for developing more robust models. Analyzing the scaling behavior of false positive rates with model size reveals a non-monotonic pattern. Smaller models show lower false positive rates, but as size increases, false positive rates rise, then fall, and rise again at the larger scales. This suggests that model capacity influences false positive rates, with mid-sized models achieving a balance between low false positive rates and high consistency. Generating new master keys involves using embedding similarity to identify sentences that can effectively attack models like GPT-4o. These new keys exploit vulnerabilities in generative reward models, highlighting the need for robust solutions. By understanding these weaknesses, we can develop strategies to enhance model resilience against such attacks. Inference time strategies like chain of thought, COT, and majority voting can enhance generative reward models, but their effectiveness varies by model and domain. While these techniques may improve accuracy in some settings, they can also increase false positive rates in others, especially in mathematical reasoning. Thus, caution is advised when applying these strategies in reference-based evaluations. Generative reward models, while promising, are vulnerable to simple attacks like non-word symbols and reasoning openers, leading to false positives. This highlights the need for more resilient, large language model-based evaluation strategies. Proposed data augmentation strategy significantly improves robustness, paving the way for more reliable artificial intelligence systems in reinforcement learning and beyond.